So hello everyone and welcome. My name is Colin Hawes. As was already said, I did research this summer with Dr. Herring K on lifetime measurements in arsenic-74 and a whole slew of other people. So the first thing I want to get into is some background on nuclear physics and also my isotope in particular. This right here is a level scheme for arsenic-74. This diagram contains a lot of information about each nucleus that they represent. And so there's a lot to go over. Each of these horizontal lines is an excited state of arsenic-74, the nucleus. Just like atoms, nuclei can have excited states. In an atom, the electron will be excited to a higher energy, but inside of the nucleus, the nucleons, which are the protons and neutrons, they'll be excited to higher energies, and then they're able to relax back down to a ground state. So each of these arrows represents that transition down to a lower energy. And that's usually seen as a gamma ray kicked off by the nucleus as it relaxes. Each of these numbers in parentheses that's accompanied by a plus or a minus, that is the total angular momentum quantum number, or the spin of each state. And then the number below that, that's not in parentheses, that is the excitation energy in kiloelectron volts of that state. The number inside of each of the arrows, that's the energy in kiloelectron volts again of the gamma ray that's kicked off. So if you took this number and subtracted this number, you'd get that one. So it's pretty simple. That's just the amount of energy it's losing. And each of these energies for the states and the gamma rays, these are quantized, which means they can only occupy discrete values. On top of that, each of the arrows, the width also contains information. The width represents the intensity. For something like this 183 transition that's very wide, we see that gamma ray being produced a lot. We see that transition occurring very often. The thinner arrows, we don't see that happening quite as much. However, there's some interesting changes that occur with arsenic-74 relative to other arsenic isotopes that have an odd number of protons and an odd number of neutrons. This here represents, these are the differences in energy between states relative to the spin of those states for a few different arsenic isotopes. Arsenic-74 is in light blue. You can see that most of these arsenic isotopes follow a nice zigzag pattern in phase with each other, but arsenic-74 has a total phase reversal, and so this is kind of confusing. And current studies that have been done suggest through theoretical calculations that this is due to triaxial deformation. This means that the nucleus's shape, it has no symmetry along any of the three spatial axes. And so from measurements of lifetime that we're trying to obtain from this experiment, we're also able to infer from those lifetime measurements the deformity of the atom. And so that's what we're kind of putting to the test. We want to see if it really has this shape. How did we produce arsenic-74? In 2014, there was an experiment done that gave us our data. They took a beam of carbon-14 that had a beam energy of 50 mega electron volts, slammed it into a nickel-62 target. This produces selenium-76. Selenium-76 then decays, shooting out a proton and a neutron, and produces an excited state of arsenic-74. We choose this reaction in particular because it has it's high energy, and so we want these high spin states of arsenic-74 to be produced. And once once we have that, it kicks out gamma rays and relaxes down to its ground state. That's not working. And then from these measurements of energy, we're detecting these just with gamma ray detectors that are surrounding this take able to put these measurements of energy into a simulation and take indirect measurements of lifetime. The simulation that we use takes into account the Doppler shift attenuation method. This just means that gamma rays that are kicked out by this nucleus are subject to Doppler shift. And so that physics needs to be taken into account. Just like if you had a car emitting a sound moving towards you, the frequency or the pitch of that sound would be increased as it moves towards you. The same thing happens to a gamma ray if the target nucleus that's emitting the gamma ray is moving towards the detector. This nucleus can be moving because as the carbon-14 hits nickel-62, it obeys the conservation of linear momentum, so it will recoil within the target. And so as it's moving, it's producing gamma rays, and so we'll see higher energies and higher frequency gamma rays than we usually would. We know that the energy will be higher thanks to a relationship from Einstein that says the energy of a gamma ray is proportional to its frequency. And so the simulation that we're putting this energy data into, it takes into account basically the time it takes for a nucleus to slow down within the target, and then also the time it takes for a nucleus just to decay on its own. So it's kind of combining this information. And then the way from these lifetime measurements that we're able to get deformation, basically we have the time that it takes for this, the survival time of each of these states. From that, we're able to infer the spreading out and orientation of protons within the nucleus. And then from that, we're able to infer the deformation of that nucleus. So this is what a lot of the data will look like once it's been shifted by this, the Doppler shift. This equation here just represents how we can calculate that energy. And this large peak, this is what we would see if the nucleus was at rest. This is that discrete energy value that is the real energy value of the gamma ray, even though we will see some spreading. The detectors that we used over the summer were the data from the 35-degree detector relative to the angle of incidence of the beam, and a 90-degree detector. The 90-degree detector will only see this large peak, and the 35-degree detector sees that shifted peak shown here. This is actually data from selenium-73, but it illustrates my point quite nicely. So this, as you can see in the 90-degree detector, these are just counts on the y-axis and energy on the x-axis. We see a nice big symmetrical peak, but we see this same peak for 35 as well as this kind of smeared out energy. And then this is actual data for arsenic-74. This is from the 1164 kiloelectron volt transition within arsenic-74's decay sequence. Each of these dots, those are the data points that I was actually inputting for the energies and the number of counts we saw at those energies. And then what we do is I vary the lifetime within the simulation that we're using until I have the lowest chi-squared value for this line fit that we have on there. From that line fit, that's where we get the lifetime measurement. For this, it was found to be 1.05. But as you can see, this fit really does not look too great. It's not fitting that smeared out side very well, and that's because this is an effective lifetime. This isn't the true lifetime of that state. An effective lifetime is the lifetime of the decay from the creation of the nucleus until the decay, and we want just that state itself. So we have to do a little bit of shaving off of other time. Arsenic-74, the 1164 transition is right here. And as you can see, it has another transition prior. It has another state up above it, and then it also has what we refer to as side feeding going on. This means that there's plenty of other states outside of this diagram we don't know about that could be feeding into the 11 plus state here. And so we need to subtract off the lifetime of the 13 plus state and any of these side feeding states until we can get the true lifetime of just the 11 plus state. So once we do these corrections, and for the side feeding, there's other estimations and calculations that we do to make sure that it works and that it's reasonable, but it's still not perfect. So this is our new corrected line fit. Still not perfect, but as you can see, it's drastically been reduced from 1.05 to 0.27 picoseconds. Now that we have these true lifetimes of each of the states, we can then use those, add them into a file, put them into another simulation, and then we're able to produce the quadrupole, I said that correctly, quadrupole deformation parameter, which is beta 2, as a function of the spin of that state. As you can see here, the blue dots are the experimental. Basically, I was able to get 3 good lifetimes from states. One of those is 1164, the other is 1406, and the other is 840. And then the orange lines, those are theoretical. Those are other theoretical calculations, and those calculations do suggest that it does have that the arsenic-74 nucleus has triaxial deformation. So as you can see, 2 points are in pretty good agreement with the theory, but the overall trend is not produced because of the second point. So what we're seeing for now is that we think arsenic-74 does have triaxial deformation, and we're seeing some agreement with theory. Does anyone have any questions? Yeah.
So you said you were able to get 3 points this summer
Yep.
to compare to the theory. Is there a plan to try and get more to see a more direct pattern emerges? Or?
Yes, so I have, after this summer, we did another experiment. We actually got to smack a few more atoms together, which in that reaction produces arsenic-74 much more favorably. Arsenic-74 isn't the only isotope produced by the carbon-14 nickel-62 reaction. So hopefully with that data, I'll be able to get a lot more counts and thus better measurements. So yeah, I would definitely like to get more measurements of the lifetimes, but those were definitely the 3 strongest out of that level scheme.
Actually, could you put up the level scheme
Yep.
one more time? So just in addition to that, the states that are lower within that ladder that you see, the arrows going down, the low lying ones, the lifetimes are too long to be measured by this method. So unfortunately, we can't continue the process down further. They're too long. But I will say there's also other detectors at a backward angle, 145 degrees, which would provide a Doppler shift to the other side of the stop peak, the low energy side. And I think Colin would like to look at that.
Yep.
He's a rising senior, so we'll be continuing this work this upcoming academic year. So we'll be looking at that too.
And the 3 points, just so everybody knows when I said, is the 13 plus state, the 11 plus state, and this 9 plus state. So those 3.
Any other questions? Please.
So on this next graph that you have,
This one?
yeah. So you said the orange line is from theory and that second point doesn't fit. So what would it mean for that second point not to fit with it?
I'm not completely sure of that, but basically what we're not seeing the trend being reproduced. So I don't know if that measurement is, I don't want to say it's faulty or anything like that because I'm not entirely sure. But as for the trend not being reproduced, I don't think I'm actually sure what that means currently. Yeah.
An optimist would say once we look at the 145 degree data, it'll be lower and the average will bring it down. But we'll see. We don't know, actually. Yeah, Steve?
Do you have an estimate of what the error bars are on that data and what the primary source of that error is?
The primary source of the theory? Or
The data.
Oh, the data. So the data
bars.
just came from these tau measurements. So the error bars won't be that big because they're basically of order for beta 0.01 on each of those. I didn't include the error bars. But yeah, each of the errors, if I remember correctly from the spreadsheet, were about 0.01 on each of
Very
those.
small.
Mm-hmm. Yeah, the error was pretty nice.
And the primary source of inserted DC is probably in the stopping powers of the nuclei as they progress through the target, as they slow and come to rest. So it's actually coming from the simulation itself.
So,
Yeah.
On the previous slide, you said that when you fit the curve to this data, you said you tried to fit the curve with the lowest chi-square value?
Yeah.
So what software did you use to do this curve fitting?
That's GNU Scope and GNU Graphy is what I know they're called, but I believe they're kind of in-house at FSU produced software.
No commercial software, these are homemade. Homemade at FSU, yeah. Great questions. Any other questions? All right, let's thank Colin again.